So our speaker on call is here, Dr. Yuting Hu. He's going to talk about Levin-Wen model with symmetries, kind of generalization of Levin-Wen model to incorporate the symmetry in rich topological phases.
Thank you for organizing this nice workshop. So today, thank you. So today I want to talk about the Levin-Wen model enriched with symmetry. So it's exactly solvable models for topological phases. So the topological phases have the properties like it has no symmetry breaking, and the ground state has topological degeneracy, and it has the fractionalized quantum numbers like fractional charge, fractional statistics, and also it has the bulk age correspondence, and we can also use the topological entanglement entropy to measure the topological order. And recently, the symmetry role in topological order has attracted much attention. So the examples are symmetry protected topological phases. They have the same symmetry as in trivial disorder phases, and there's no long-range entanglement. So in the bulk, there's no fractional statistics. And also, it's stable against local perturbation, preserving symmetry. Examples are topological insulators for them phase in spin one chain. And recently, symmetry enriched topological phases attract much attention, and they have richer structure in topological order. For example, they have the phenomenon of symmetry fractionalization, and recently there are more developments, new developments go beyond such phenomenon. And in today's talk, I want to show the theoretical approach to study these topological phases. So if the effective theory approach to the topological phases, usually we use the topological quantum field theory. For example, the Chern-Simons matter field theories and the pure Chern-Simons field theories. But in today's talk, I want to discuss the discrete exactly solvable model. And particularly, this Levin-Wen model, it describes a large class of non-chiral topological faces. And I will introduce the Levin-Wen model first, and then I will show how to enrich the model with symmetry. So I will talk about how to extend this model. So Levin-Wen model is defined using the fusion category, and if we extend the fusion category to the multifusion category, then we may have the global symmetry in the model. And then next I will talk about the symmetry enriched phase, topological phase, by starting the Levin model with this extension and discuss the promotion to the gauge theory. And lastly, I will discuss the ground states in such models on torus to study the properties of the symmetry enriched topological phases. So first, what is Levin model? I will introduce the simplest example of the Z2 model. Is also known as Kitaev's torical model, or it's known as the Z2 gauge theories. So it has two terms. The Hamiltonian has two terms, and the Hilbert space is defined on a two-dimensional lattice. So it can be defined on a square lattice, but for the purpose to genetically define the Levin model, we use the trivalent graph. So the Hamiltonian has two terms. The first term is defined as vertices. So we have the sigma, we have the polarimetries on the three links going into this vertex. And the second term is the sigma x defined on the boundary links of the plaquette. So this model is exactly solvable. That and we will observe that these two operators Q and E, they are mutually commuting with each other, and all of them are projections. So on a torus, the ground states are degenerate. The degeneracy is 4. And these degenerate ground states are one-to-one corresponding to the particle species in the bulk. So quasi-particles has 4 species. This is vacuum, this is the Z2 charge, Z2 flux, and the charge flux combinate. So on the graph, it can be illustrated like this. The flux is leaving at plaquettes, and the charge are leaving at the vertices. So in general, the Levin model can be defined on a trivalent graph on a closed surface, and the input data, the Z2 spins, can also be generalized. This Z2 group of the polarimatrices can be generalized to arbitrary finite groups or quantum groups, and more generally, the model can be defined using the input data from unitary fusion categories. Now I will explain briefly what I mean by the unitary fusion categories. So by this generalization, we can view the Levin model as a discrete topological gauge field theories with the finite gauge groups or gauge quantum groups coming from these input data. So why generalization to quantum groups and more generated unitary fusion categories? Because it's a natural language, it's a natural structure to describe the states involving the anions, the anionic matter. So I will spend a few minutes talking about the input data to define the level model in a generic way. So the fusion category, by fusion category we mean the tensor description. So fusion category is defined mathematically, but to define the model we use tensors. So to start with, we have finite number of string types. So usually we label these string types by integers, or sometimes maybe half integers. And with these string types, we have also fusion rule or branching rule satisfy these three conditions. So the meaning of these fusion rules has an intuition coming from the representation theory. For example, in SU2 representation theory, if you have the for SU2 representation theory, you have the irreducible representations, 0 spin, 1/2, 1 spin 1, spin 3/2. Then you have the coupling of the spins. For example, you couple the spin 1/2 and spin 1/2. Then the total spin, the possible total spin is either 0 or 1. So this capital N is this rule to couple A and B, and to find and to check whether this zero is the trivial, the identity representation theory. So then with these string types and the fusion rule, we have the final data, which is called a signature symbol, which characterizes the fusion category. So the signature symbol, we will use some symmetry condition on the signature symbols here. It's called a unitary symmetrized signature symbol. So when I say symmetrized, then they satisfy these conditions. So we already know this in the SU2 representation theory. There are some conventions, some phase conventions to fix the signature symbols. Or in lower level, the Clash-Gordon coefficients. We need some phase conventions to fix these data. Then the Hamiltonian can be defined in terms of these data. So it involves a lot of tensors, but the basic properties from the Z2 model, they survive. For example, the Q and B, they are mutually commuting with each other, and they are projection operators. So as a result of these properties of local operators Q and B, we see that the ground states are the mutual eigenvector of Q and B. if at some plaquettes, P prime or at some vertices, Q and B are equal to 0, then it's excitations in the model. And the elementary excitations is called quasi-particles. So in general, we will draw this through a string, and this and the quasi-particles are living at the two ends of the string. So what's the meaning of this string? So so from the ground states, we can generate an excitation by a quasi-particle creation operator. So when we create a pair of quasi-particles, we can move them, and so they can go far away from each other. But there is some topological property of these quasi-particles. That means if we have we create a pair of quasi-particles, and finally they arrive at these two places, then the final state is the same. It doesn't matter along which path you move these quasi-particles. So this is a topological property of the quasi-particles of the excitation. So in general, the quasi-particles are characterized by the quantum double of the input data. So here the capital Z means quantum double. It's a mathematical notation. So in physics, quantum double means it's the charge flux complex. For example, in Z2 case, this C is we can view this as the Z2 group representation. So you have you have two objects. You have a trivial one, and you have a Z2 charge. That's how you input the data to define the Levin model. And the quantum double means you have a Z2 charge, and you have Z2 flux, and also the charge flux complex. So and this, in general, this procedure can be generalized to any unitary fusion categories. And so what makes this Levin model as the model for topological phases? An important feature of this model is the topological it's the topology preserving symmetry. So for example, you can the ground states are the fixed point states of the local unitary transformation, or also known as the Pachner move, which change the structure of the graph. In continuum case, it's a metric transformation. So this topological feature will lead to the topological observable, ground state degeneracy, and modular matrices S and T, which we can use to characterize the topological phases. So now, so basically, this is a Levin model I want to introduce. And from now on, I want to talk about the extension, the multi-fusion category extension. So for fusion category, we can understand it as the representation theory, and so I will use the whiteboard sometimes to have this screen. So the fusion category, we can understand it as the representation theory that each string type is understood as the representation, and there is always a trivial zero, which is corresponding to the identity representation, or in but if we generalize, if we replace this zero, which has the property, if it couples to any representation J, it must be equal to J. So that's the unit property. So if we replace this unit by a set L0, for example, we say 0 and 1. And we also do this replacement in the fusion rules. Then we have 0.
Is this one in the original category or not? Or some new stuff? This one in this L naught. Is it in the original category? Is it an object in the original category?
So here, I'm not trying to construct a new category from the original one. I'm trying to define the. I'm trying to introduce a new multi-fusion category and just start with this one. So.
Oh, this is not based on the.
Not based on.
Okay. Any existing category.
Yeah. So. So this is the general definition. So maybe I will finish this explanation and then go to the example to get an intuition of this as 0. So by replacing 0 by a set, by a label set as 0, I mean this entire set I viewed as the identity representation. So
Is there any projection involved in this tensor product or quotient? Is any relation between is any tensor product between 1 and J itself, these two objects? Or?
Yes.
So then there will be some projection or involved in this definition, right?
Yes. For example, Yes, so my answer is yes. And actually, this is a good example. Use.
But suppose you have an AA star fusion, what do you get?
A star fusion.
Yeah.
You get only one object in this set. So like in this L0, this L0 has two objects. The A star.
But which one is
Depends. That's the property of the A. So that means A has a grading. It's graded by the object in this set.
So if you do AA star equal to 1 plus 0, that's you have a problem with that. So since that
That is not. Then this L0 cannot be called a unit. It's no longer a multiplication category.
But A tensor with its dual should include L0, right? There's still a definition of inverse, right?
Yes.
So A tensor A star should at least include one copy of this L0.
Yes. It's equal to one copy. One copy inside L0. Not all of them, but just one.
Not L0, but just one.
Yes. So by looking at this definition, it will be too abstract to get an intuition. So I will use this example. This matrix. So for example, N2. The two matrix means you have you can have a 2 by 2 matrix, but each matrix element is viewed as a string type. So the fusion rule is given by the matrix product, matrix multiplication rule. So for example, for N2, you have 4 objects. And matrix multiplication is given by so this is one example of the fusion rule. So actually, the fusion rule for all objects are determined by the multiplication. So in general, it will be the ij entry of the matrix tensor KL entry of the matrix. And what you get is the object disappears if j is not equal to k. And if j equals to k, then you can do the multiplication. Then you get IL. So this is the general fusion rule of two matrices. So this is the definition of the multifusion category, but what's the meaning in Levin-Wen model? Or what does it imply